Next, let's try to take a look about the second example of the EM waves, which is the microwave. So this is the wavelength widely used in our daily life when we try to heat the food or for the communication. And the frequency of the microwave is from 10 to power 10 to power 9 to 10 to power of 12 Hertz. And since this is a big number, but still it is considered a lower frequency. And the wavelength is from 1 millimeter to 30 centimeters. And the reason I particularly mention about the wavelength here is because in the experiment, people find out, based on the water molecules, the structure of that, and the size of the water molecules, they have a very good interactions with the EM waves. So in other words, it means that when the microwave hit on the water molecules, all the energy will be given to the water molecules, and the energy will start to vibrate the particles within the water molecules and make them feel hot, getting hotter and hotter, and the temperature will be increased. And that's the reason why your food become hotter and be heated. And intrinsically, it is related to the structure of the water molecule is polarized. And this kind of extra energy given to the structure will let the negative and charged particles start to oscillate more. So now let's look at the third kind of the EM waves, which is the so-called infrared waves. So people people cannot see that, but people can feel that as a heat. And it doesn't really hurt your skin, but when you get exposed to the environment with the infrared waves, you will feel warmer. So the frequency of the infrared is from the 10 to power 12 to 10 to power 14 Hertz. And actually, because human beings feel that as a heat, so when you try to use the infrared detectors, what you are going to see is about the distribution of the charge. So the hotter the area, and the bigger the frequency will be. So you can try to connect the concept of heat to the wavelengths of the infrared wave. So now let's take a look about the second conceptual quiz today. So now, assume that your eyes no longer receive the optical light. Instead, you receive the infrared. So what will you see around the room now? So the answer is, if you take my words, try to understand the infrared as the concept of the temperatures. So if you look at the sky, all the stars with a very high temperature, 60,000 Kelvin or even higher depending on the stars, but the space in between is pretty cold. So you will see a bunch of bright spots in the sky, but dark everywhere. So that's the reason it is related to the temperature. So infrared is a very useful tool people will build on the surface of the Earth to detect the signal from the universe. Now the fourth category is the visible light, which everyone knows. This is the wavelengths and the frequency the human eyes can really see, and this is how the image was formed in our eyes. But you'll find out that the range of the frequency is actually pretty narrow. It is from 4.3 to 7.5 10 to power 14 Hertz. So actually, among the broad spectrum of the EM waves, only a very narrow range can be seen by the human eyes. And as the color just give you a sense of feeling, so the red is considered the wave with a longer wavelength, and the violet is the color people will consider it is the wave with a shorter wavelength. So that's the reason in our previous discussion that we say that when the wavelength was stretched, become longer compared with the normal one, we say it is redshifted. But if the wavelength becomes shorter, we say it is blue shifted, and that is where the language is borrowed from. Now let's take a look about another one, the ultraviolet light. So ultraviolet is the light with very high frequency from the 10 to the power 14 to 10 to the power 17. They can cause the damage and burning to your skin and the body. So that's the reason normally people will take the sunscreen when they go out to have the sun bath. And the light from the sun mostly was the UV ray, which is ultraviolet. So they carry a very big energy. And two more, the X-rays. So X-rays has even higher frequency. So that's the reason when you went to the hospital to take the X-ray, you are required to take in a shelters making by the metals. Because if you were exposed to the X-ray too frequently and with a huge amount of magnitude, it will hurt your body. And this is usually used for the medical image. So what will happen is that if you take to the previous spectrums, which is this one I showed you before, so X-ray, the wavelength of that is about the size of the atoms. So what does it mean? It means that when your body was exposed to the X-ray, X-ray will very unlikely to be scattered out until they interact with the atoms. So any structures bigger than the size of the atoms will be shown. So therefore, you can see that the X-ray will hit your hand, but not everything was shown. Yeah? They were passing through a lot of the structure of your hands, but eventually they will be reflected by the structure at a scale about atoms or a little bit bigger. So they can show you the very delicate structure of your hands instead of just showing the skin and all the cells. So it can show you the skeletons. But for sure, they're also involved with the properties that which material has a better interaction with the gamma rays. And gamma ray was also a very good source when we try to detect the explosions of the galaxy, like the supernova. So what happens is that you will launch a satellite, and the explosions of the gamma ray will propagate to the detectors. And because the wavelength is so small, so they seldom interact with other particles. So this is a very good source for the detections. So finally, let's take a look at the final one, the gamma rays. So gamma ray is the highest frequency among all the spectrums. It is above the 10 to the power 20 Hertz. So they are extremely energetic, which means if you are exposed underneath the gamma ray with a short period of time, your skin will be damaged, your organs or anything, it's the cell. So especially they are pretty damaged, they produce a big damage to the living cells. So sometimes people will use this one as a source to kill the tissues, the fatal tissues, or the for example, like the harmful stuff. So now let's try to summarize. So we have studied about the spectrums of the EM waves, from the long wavelengths to the short wavelengths, from the short small frequency to the high frequency. And here I give you a sense of feeling how big, how long the wavelength it is. And for sure, if you consider in the language of the temperatures, then the higher the frequency, they carry the bigger energy, the temperature will be higher, and the lower the frequency, the lower will be the energy it is. So now let's take a look about the third conceptual quiz today. So which one has the longest wavelength? And a trivial answer is radio waves, because they have the shortest frequency. So the wavelength should be longest. And finally, let's talk about the property of the materials. So the interaction between the light and the material is very similar to the sound wave to the material. So first, the light will hit on the matter, and matter is made of the bunch of the particles. So they will force the electron within the particle to vibrate. And these electrons will then hit the second one. So you can see from the diagram here, the light comes in and hit the first one and vibrate the electron within the first atoms, and then hit the second one, and the energy was propagated out through. So let me show you videos how the electron in atoms of the glass are forced to vibration due to these kind of transitions. So you can see that you can treat them like this is how the light was transmitted through the interaction of the electrons among the galaxy. So you can see that the light comes in here and excited the electron here, and the energy was transmitted through. And when the energy was transmitted through, they produce the light, and light just passing through. But intrinsically, we don't need any particle to propagate the light. This is an intrinsic difference compared with the EM waves and the sound wave. So we don't necessarily need the particles to propagate the wave, the light, the EM wave. However, when they interact with the particles, the light as a photon, as a particle, will be absorbed by the particles, electron in the glass, and they will start to vibrate. And the electron then will vibrate, emit another photons, and transfer the energy to the second one. And this is how the thing was propagated through. So you can using the language of the particle such that when the light tries to pass through the glasses, it is just a photon interact with the electrons, and photon disappear, and electrons start to vibrate, produce another photon, and the photon hit the second electrons and propagate. So why we're going to introduce that? So even though the light doesn't need any material in order to propagate, but they can propagate at different material, and the speed of light will be different. So in the vacuum, the speed of light is fastest. But when you propagate the light in the atmosphere, when you start have the particle like the air particle, the speed of light will be slowed down. So in the atmosphere, the speed of light actually is slightly less than c. But for the light propagated in the water, it will become even smaller, and depending on the structure of the material, the more dense of the material, the harder for the light to be propagated.